In the last session, we were talking about how to do the manual design of a combined footing. So we have seen a problem statement where we are provided with two square columns. Each column is carrying different intensities of load, that is 300 and 500 kilonewtons of load. And the center to center distance between the two columns is limited to 4 meters, along with the bearing capacity of the soil is 100 kilonewtons per square meter. Whereas we need to design a rectangular combined footing and keeping the width as a constant, that is 1.5 meter. The length of the footing can be anything, but width of the footing is limited to 1.5 meters, and the grade of concrete is M20 and grade of steel is Fe415. So first we have defined the loads and then we have defined the dimensions of the footing based upon the area calculation. And then we have discussed this concept called center of gravity of the load. And then we have found out the shear forces and bending moments, that is maximum shear forces and maximum bending moment. Based on the maximum shear forces and maximum bending moment, we have found out the depth required for the footing. That's what we have seen in the last session. Okay, so the depth provided is 392 mm and the overall depth that we have provided is 450 mm. Right. So from here, what we are going to do next is, let us calculate the two-way shear first. I'll tell you the reason why we are calculating the two-way shear. First, let us calculate the two-way shear. So before calculating the two-way shear, let us understand why we need to calculate the two-way shear. So the two-way shear is calculated based upon a criteria in order to check whether which column is experiencing, that is tau v less than tau c condition or not. So if tau v is less than tau c, then it is safe in shear, that is in two-way shear. If tau v is greater than tau c, we have to modify the depth of the footing. That is what we know, right? Right. So the next thing is checking against or check against two-way shear. We know that two-way shear is also called as punching shear. The two-way shear is also called as punching shear, right? So let us find out how to work with the two-way shear. We know that the two-way shear, in order to calculate the two-way shear, we should know here there are two columns that are available. Okay, one column is having a load intensity of 300 kilonewtons and one column is having a load intensity of 500 kilonewtons. Now, what is the critical section for two-way shear? The critical section for two-way shear lies at a distance d by 2. Okay, the critical section for two-way shear, okay, for two-way shear lies at a distance d by 2 from face of the column on all four sides. Okay, on all four sides. Right. Now I'm telling that critical section lies at a distance d by 2 from face of the column. But here, how many columns we have? Two columns we have. But which column critical section we have to consider? Okay, in order to calculate the punching shear or two-way shear, we know that two-way shear acts at a distance d by 2 from face of the column. But here, if you clearly observe, we are provided with two columns. This is the first column and this is the second column. Now, which column we have to consider in order to calculate the two-way shear consideration? So for that, what we have to do is we have to find out the maximum shear force. Okay, we have to find out maximum shear force. So how will you find out the maximum shear force? In the last session, we have found the maximum shear forces. Now, if you observe all these values, maximum shear force value is lying at on which column? At which column we are getting the maximum shear force? If you observe this shear force diagram, so here we have column A and here we have column B, that is column 1 and column 2. Now, which column is experiencing the maximum shear force? So column 1 is experiencing a shear force of 66.67, whereas column 2 is experiencing a shear force of 300 kilonewtons. So we know that from this shear force diagram, the column 2 is experiencing the maximum shear force. Okay, the column 2 is experiencing the maximum shear force. So what we have to do is we have to do the two-way shear calculation for column 2 only. Why? Because since column 2 is experiencing the maximum shear force, if you design the two-way shear force for this maximum shear force, then obviously this column 1 will also be within the limits only. So always remember, two-way shear calculation, especially in the design of combined footing, has to be calculated based upon the maximum shear force. Whichever column is experiencing the maximum shear force, that column we have to consider, and for that column only, we have to consider the two-way shear calculation. And two-way shear calculation will be considered for column 2, right? That we know. Just give me a second. Yeah. So two-way shear calculation shall be calculated for column 2. So this is actually the column 2. Okay, this is actually the column 2. So if you draw the diagram of column 2, suppose let's say this is my diagram. Okay, this is the diagram of critical shear section from the column. So what will be this distance? So what are the dimensions of column 2? The column 2 dimension is 300 by 300 mm. Okay, the column 2 dimension is 300 by 300 mm. Now, what will be the distance? I was telling that the critical section will act at a distance d. Okay, it will act at a distance d from face of the column. So this is the face of the column. Okay, this is the face of the column. From face of the column, the critical section will be lying at a distance d by 2 from face of the column. Okay, d by 2 from face of the column. So we know the dimension of the column, which is 0.3 meters. Okay, that is 0.3 meters. Then what will be this distance? This distance will become, so this side d by 2, okay, d by 2 plus 0.3 plus d by 2. So d by 2 plus d by 2 is d. So 0.3 plus d will be the total distance of the critical shear section, or the total dimensions of critical section. So this side it is 0.3 plus d, and this side also it will be 0.3 plus d. So that's how we are going to calculate the punching shear based upon the maximum shear force calculation. So here we are going to calculate the maximum shear force based upon, I mean, the two-way shear force based upon the maximum shear that is obtained. So two-way shear, okay, in combined footing design, in combined footing design, the two-way shear, critical section, the two-way shear critical section shall be considered for the column whichever is experiencing the maximum shear force. Yes, maximum shear force. In this case, the maximum shear force is acting at, or is acting at column 2, that is C2. Okay, so hence we need to calculate, or we need to check the two-way shear calculation for column 2 only. Okay, I hope it is clear. Right. So let me have the diagram first. I have already drawn it. So let me just give you the diagram. Right. So this is the diagram that I was talking about. Right. So we have two columns, that is column 1 and column 2. We know that on column 2, the maximum shear force is happening. So here I have drawn only the column 2 diagram. Okay, this is just the column 2 diagram. So the dimension of column 2 is 0.3 meters, and this side also it is 0.3 meters. It's a square column. So the total distance is d by 2 from here, 0.3 plus d by 2. That is critical section length. So therefore, this distance will become 0.3 plus d, and this distance will also become 0.3 plus d. So from this, we need to calculate the shear force. Shear force capital V equals to, what is the total load on the column 2? The total load on column 2 is 500 kilonewtons. Okay, the total load on column 2 is 500 kilonewtons. So therefore, capital V equals to 500 minus, what is the upward soil pressure? Upward soil pressure is 88 point something, 88. Yeah. So here you can see upward soil pressure is 88.89. So 500 minus 88.89, which is the upward soil pressure, into 0.3 plus d. So this side we have 0.3 plus d, and this side also we have 0.3 plus d. So 0.3 plus d whole square. So 0.3 plus d. What is d? The effective depth. What is the value of effective depth? Here you can see So the effective depth value is 392 mm. So that equals to 0.392 whole square. Okay, 0.392 whole square. Why we are multiplying with whole square? It is because we have 0.3 plus d along this side and 0.3 plus d along this side. It's a square section. Okay, right. So once you solve this equation, you're going to get the shear force value. That is capital V value, which will be 457.43 kilonewtons. From this, we can calculate the ultimate shear force, that is Vu equals to 1.5 times of 457.43. So that equals to 686.15 kilonewtons. So that's how we can calculate the ultimate shear force. Now, in two-way shear calculation, we have to calculate the perimeter length also. So perimeter length of shear area. So we know that we are representing it with B dash. So B dash equals to, okay, B dash equals to 0.3 plus D. So how many sides are there? 4 sides are there. So this is one side, second, third, and fourth. So 4 into 0.3 plus D. Okay, 4 into 0.3 plus D. So I'll just make it as 300 mm, which is the dimension of the column, plus D. D is the effective depth, that is 392 mm. So that equals to, we are going to get the value as 2768 mm. That's the total shear area. Now let us calculate the nominal shear at critical section. Same concept, nothing is changing here. Okay, only the shear force calculation is getting changed. Shear force and bending moment calculation. So nominal shear at critical section, tau V equals to, we know the formula, Vu divided by B dash into D. Okay, Vu divided by B dash into D. What is Vu value? Vu is 686, okay, 686.15 into 10 cube divided by B dash. What is B dash? B dash is the perimeter area or perimeter length of shear area, which is 2768 into D. What is D? Effective depth. That is 392 mm. Okay, 392 mm. So from this, we can get the nominal shear at critical section, which will be 0.6323 megapascals. Okay, now we got the nominal shear. Now let us calculate the tau c value. Okay, tau c value. So how to calculate the tau c value? So we know that as per IS 456-2000, okay, as per IS 456-2000, if you remember the clause 31.6.3, page 58, if I'm not wrong. So 31.6.3 from page 58, we know how to calculate the shear at critical section. So shear at critical section equals to tau c into Ks. I hope you remember this formula, tau c into Ks. So how to calculate the value of Ks? Ks equals to 0.5 plus beta c. So I'm not going into the details of codebook because we have already seen in the previous problems. So you can refer that directly. So 0.5 plus beta c. But how will you calculate the beta c value? Shorter side length of column. Okay, shorter side of column divided by longer side of column. Longer side of column. So what is shorter side of column? Which column we have to consider? Column 2 only. Why column 2? Because we know that the maximum shear force is being experienced by column 2 only. So you have to calculate, or you have to take the dimensions of column 2. That is 300 by 300 mm. That equals to 1. That's beta c value. So now Ks equals to, okay, Ks equals to 0.5 plus beta c. What is beta c value? 1. So that equals to 1.5. So if Ks value is greater than 1, okay, so since Ks value is greater than 1, we have to consider Ks equals to 1 only. If Ks value is less than 1, then whatever value you are getting here, suppose let's say if Ks value you are getting it as 0.65, then you have to consider the Ks value as 0.65 only. In any case, if it is greater than 1, then you have to consider only it as 1 only. Right. So now let us calculate the tau c value. So how to calculate tau c value? Tau c equals to 0.25 into root fck. Okay, 0.25 into root fck. So I'll just make it as 1 by 2, power 1 by 2. So from this, we can get the tau c value. So how to calculate tau c value? 0.25 into root fck. Fck value is grade of concrete, that is 20 divided power 1 by 2. That is root. So once you solve this equation, you're going to get the value as 1.118 MPa. Right. So now you can check whether tau v is less than tau c or greater than tau c. What is tau v value? 0.63. Tau c value is 1.118. So tau v is less than tau c only. So tau v is less than tau c. So therefore, provided depth is safe in punching shear. Okay, provided depth is safe in punching shear. So now what we will do is we have to find out the reinforcement. So especially in the combined footing design, reinforcement calculation is the very critical part, or the most important part, you can say. So let me write that one. So design for reinforcement. So the next step is design for reinforcement. Right. So how to find out the reinforcement? So in order to find out the reinforcement, first let us understand the bending moment diagram first. So if you see the bending moment diagram of the column 2, let me draw that. Yeah. So if you see the bending moment diagram, not just the bending moment diagram, I'm just writing the path here. Let us understand that first. So this is how the combined footing is available. Right? This is how the combined footing is available. Now, how bending moment will be acting here? So here, this portion we know as the stiff portion. Exactly under the column, whatever the area that is available, this portion will be very stiff. This portion is also very stiff portion. The only not so stiff portion is the cantilever portion. Now, how bending moment will happen? Here, bending moments will happen in a different way. Okay, bending moment will happen in a different way. So for that, what we have to understand is we have to understand the bending moment pattern of the shear foot of the combined footing. So how it acts. So it will be in this way. So let me draw that. So this is column. So the bending moment here at the edge will be like this. And here at the central portion, the bending moment goes in this way. Okay, it goes in this way. And then the columns will be there. Okay, here one column and here also one column will be there. And then it goes in this way. Okay, if you see the diagram. Yeah, so this is how approximately it will be. I hope you are getting the pattern of the bending moment diagram. So here, which sides are compression forces, which sides are tensile forces? So this zone is a compression zone, and this zone is also a compression zone, and this zone, the central portion, is also a compression zone at the bottom. Okay. Now, which are the tension zones? The tension zones are, so this is the tension zone. Okay. And here also it will be the tension zone. It's not a straight line, it's actually a curve. And here also it will be a tension zone. So where we need to provide the reinforcement, wherever the tension zones are available, there we have to provide the reinforcement. Okay, main reinforcement has to be provided in tension zones. That we know. So in the tension zones, we have to provide the reinforcement, and in the compression zones, we have to provide the minimum reinforcement. Okay, in the tension zones, we have to provide the maximum reinforcement or the reinforcement according to the design consideration. But in the compression zones, we have to provide at least minimum reinforcement criteria, right? So now, how many tension zones are there? We have three tension zones. One is at the center of top, okay, mid span at the top, and the second one is at the bottom, okay, of column 1 and bottom of column 2. So these are the three tension zones. So for all these three tension zones, we have to find out the reinforcement. Okay, for all these tension zones, we have to find out the reinforcement. And then wherever the compression zones are available, along compression zones, we have to provide the transverse reinforcement. Okay, transverse reinforcement has to be provided in the compression zones. I'll show you that, but first let us understand the tension zone reinforcement provisions. So from this diagram, it is very clear that tension zone reinforcement has to be provided at the center of column 1 and column 2, that is at top. Remember, this reinforcement has to be provided at the top. And at the bottom of column 1, we have to provide the tension reinforcement, and bottom of column 2, we have to provide the tension reinforcement. So bottom is nothing but it goes in this way. So here we are going to provide the reinforcement at the bottom, and here we are going to provide the reinforcement at the top. This is how the reinforcement diagram looks like. Right. So from this, I hope this diagram is clear. So please make sure to remember this particular diagram. Let me just take a screenshot of this one because we need it for another cases. Right. So let me remove this diagram. Right. So how to provide the reinforcement or where to provide the reinforcement? So the first scenario is longitudinal reinforcement. Longitudinal reinforcement. Longitudinal reinforcement at mid-span. Okay, at mid-span. Basically, this is at top. Yeah, at the top you can say. So this is basically which type of reinforcement? It's a tensile reinforcement. So longitudinal tensile reinforcement at a mid-span, that is at the top portion. So we know the moment value. What is moment value? If you check down the moment values, let me check that. Yeah. So what is the maximum moment? Maximum moment is 187.49. So based on this moment only, we have to do the design calculation. So you should not consider 16 and 150. Why? Because we always need to design the reinforcements for maximum moments only, not for the moments at that particular point, right? So the maximum moment is 187.49. So I'll just consider it as 187.5. Okay, maximum, let me write that, maximum moment. Maximum moment, capital M equals to 187.5 kilonewtons meter. So for this, you can do the ultimate moment, that is 1.5 times of 187.5, that equals to 281. Okay, 281.25 kilonewton meter. So basically, the value is coming in positive, so it's a hogging moment. Okay, hogging moment, right? So based on this moment, we have to find out the area of steel. So how to find out the area of steel? So we have the formula, that is AST equals to 0.5 FCK divided by Fy, this one. Yeah. So based on this formula, we have to calculate the moment AST value, that is area of steel. Right. So from this, the FCK value we know, that is grade of concrete, that equals to 20 MPa, and Fy value also we know, which is grade of steel, that is 415, and maximum moment Mu equals to 281.25 into 10 power 6. I'm just converting into kilonewton meter, Newton mm. Right. So 281.6 Newton mm, and then the value of B, which is width. Okay, width V equals to 1500, and the depth value D equals to 392 mm. 1500 mm and 392 mm. Width of the footing is 1500 and depth of the footing is 392 mm. Right. So how this 1500 is coming? Because in the question itself, they have mentioned that the width of the footing has to be limited to 1.5 meters. So therefore 1500 mm. Right. So from this, if you just substitute the values, you're going to get the area of steel, that equals to 2151.54 mm square. 2151.4 mm square. So that's how we can calculate the area of steel. So this is basically the design requirement. Let me write that, design requirement. Right. So now what we have to do, minimum reinforcement provision. Minimum reinforcement. So how to provide the minimum reinforcement? That is AST minimum. Let me hit this. Yeah. So AST minimum. What is the formula for provision of minimum reinforcement? 0.12% B into D. That is capital D. So that equals to 0.12% into B. What is width of the footing? 1500 mm into the overall depth of the footing is 450 mm. That is what we have considered. So that equals to 810 mm square. That's the total area of a minimum reinforcement. Right. So the design requirement is 2151. Minimum we have to provide 810 mm square. So let us provide the diameter of bar. Okay, providing diameter of bars as 16 mm and cover as 50 mm. That we know. Okay. So from this we can calculate the spacing value. So how to find out the spacing value? Spacing required. Okay, spacing required equals to. So how to find out the spacing? Area of one bar. So how to find out area of one bar? Pi by 4 into d square, where d is 16 mm. So if you do pi by 4 into d square, the value will be 201.06. Okay, that's area of one bar divided by the total area of reinforcement. So that is 2151. So 2151.54 into width of the footing, that is 1500 mm. So if you solve this one, we are going to get the area as our spacing as 140.132 mm. So we know that I told you reduce either 20 or 25 mm. So therefore provide a spacing of 125 or 120 mm. That's completely up to you. 125 mm center to center. So that's how we can decide the spacing. Right. So based upon the spacing value, we can decide the total area of steel provided. So area of steel provided, AST PROV. I'll just make it as provided as PROV. So area of steel provided equals to, so how to find out area of steel provided? Capital total area of one steel bar, that is 201.06, divided by the spacing value, that is 125 mm, into the width of the footing, which is 1500 mm. That equals to 2412.72 mm square. So this much amount of reinforcement we are going to provide with a spacing of 125 mm. Okay, with a spacing of 125 mm, we are going to provide this much area of steel or this much size, this much steel. Now we know in the two-way shear calculation, we always have to consider percentage of steel, that is PT. PT equals to capital AST divided by B into capital D. So what is capital AST? 2412 provided area. Okay, 2412.72 divided by B. What is B? Width of the footing, that is 1500, into D, that is overall depth. Overall depth is taken as 450 mm. Once you solve this one, you are going to get it as 0.36%. Okay, 0.36%. So that's the percentage of steel. So like this, we have to calculate the steel at, first we have calculated at the top. Similarly, we have to calculate here. Okay, we have to calculate at the bottom of column 1 and also at the bottom of column 2. Right. So first let us do the calculation of reinforcement at the bottom of column 1. Right. So what is the moment at column 1? Let me write that. Longitudinal tensile reinforcement at mid, instead of midspan, I'll just make it as at bottom of, okay, bottom of column 1. At bottom. Right. So longitudinal tensile reinforcement at bottom of column 1. So what is the moment at column 1? Let us check that. Moment value at column 1. Yeah. Here you can see. So moment value at column 1 is 16.667. So let us take the moment as 16. That is capital M. Moment equals to 16.67 kilonewtons meter. Okay, 16.67 kilonewtons meter. So if you want to find out the ultimate moment equals to 1.5 times of 16.67. So that equals to 25 kilonewtons meter. So it's basically a sagging moment. Okay, sagging moment. Right. So from this, again, we have to find out the area of steel by using the same formula, but with different values. So moment mu value will get changed. What is mu here? 25. Rest all the values remain same. What is B? B is width of the footing. That is 1500 mm. What is D? D is effective depth. Same like this here only. Okay, let me copy and paste it. Right. So moment value only will get changed, which will be 25. B and D, everything remains same. So therefore, AST, that is area of steel, equals to 177.84 mm square. That's the area of steel value. Right. So this is basically the design requirement. Okay, design requirement. Okay, this is basically the design requirement. So minimum percentage of steel. Okay, minimum percentage of steel. So how to find out minimum percentage of steel? AST minimum equals to 0.12% B into D. So same formula again. So 0.12% B into D. So I'll not write this. I'll just copy and paste this. So 0.12%, B is 1500 mm and D overall depth, capital D equals to 450 mm. So we are getting this. So here, so since it's bottom reinforcement, okay, since the reinforcement is provided at the bottom, either we can decrease the sizes of the bars or we can provide the same size of bars. But the general practice is at the top, we are going to provide the larger diameter of bars, and at the bottom, we'll provide a smaller diameter of bars, maybe plus or minus 4 mm or minus 2 mm is fine. Okay. So what is the diameter of bar provided at the top? At top is 16 mm. So you can either provide 14 mm diameter bar or you can also provide 12 mm diameter bar. Plus or minus 4 mm is fine. Don't go more than that. Okay. So let me do that. So at bottom, let me write it as note. So at bottom face, sorry, what happened? Yeah. At bottom face, the size of bar, can be reduced. It can be reduced up to 4 mm. Okay. So therefore, provide, let's say for 16 mm, right? Here it will be 12 mm diameter. Therefore, provide 12 mm diameter bars. Okay, therefore provide 12 mm diameter bars. So area of one bar. Okay, area of one bar of size 12 mm. What will be the area of one bar? Area AST, that is pi by 4 into d square. So if you do pi by 4 into d square, the area of one bar of diameter 12 mm is 113.09 mm square. That's the area of one bar. So from this, we can find out the spacing. Okay? Spacing S equals to, or spacing required equals to, area of one bar, that is 113.09 divided by the minimum percentage of steel. What is minimum percentage of steel? 810 mm square. Okay, divided by 810 into the width of the footing. What is width of the footing? Width of the footing is 1500 mm. Okay, so if you solve this equation, you will be getting it as 209.44 mm. That's the spacing value. Okay, so we can reduce it to 200 mm, or you can reduce it to 180 or 190 also. That's up to you. Okay, let's provide it as 200 mm. So therefore, provide the spacing of, okay, provide a spacing of 200 mm at bottom face, of column 1. So let us find out the area of steel provided. So area of steel provided, that equals to AST provided equals to area of one bar, that is 113.09 divided by spacing, that is 200 mm, into the width of the footing, that is 1500. So if you solve this one, the value will be 848.18 mm square. So that's the area of steel provided. So again, we have to calculate the percentage of steel, that is PT equals to AST by BD. AST value is 848.18 divided by B into D. B is width of the footing, that is 1500, into the overall depth, which will be 450 mm. So if you solve this equation, it will be 0.1256%. That's the steel. So similarly, you can also calculate the value for area of longitudinal tensile reinforcement under column 2. That I'll keep it as a reference for you, so you can solve it on your own. So I'll be leaving this as blank. So longitudinal tensile reinforcement at bottom of column 2. So you try to solve this one. Only the moment gets changed. Everything remains same. So what is the moment at column 2? You can see the shear bending moment diagram. So the moment at column 2 is 150 kilonewtons per meter. Okay, let me just write that one so that you don't get confused when you're solving. So moment at column 2, that is capital M equals to 150 kilonewtons meter. So from this, we can calculate the ultimate moment, that will be 1.5 times of 150, that equals to 225 kilonewtons meter. So you can solve with this one. I hope you can solve. So again, this is also a sagging moment only. Right. So from this, you can calculate the area of steel, spacing, everything. Same like this, you have to calculate. I hope you can calculate this one. Right. So that's the reinforcement, the tensile reinforcement, you can say. So tensile reinforcement at top face and also at the bottom faces of column 1 and column 2. Now, what we have to provide is we have to provide the transverse reinforcement. So where we have to provide the transverse reinforcement has to be provided along the width of the footing. Okay, transverse reinforcement means we have to provide the reinforcement along the width. So transverse reinforcement along width of footing. This one also I'll do it. I'll do for one or two later. Remaining you can do it. Right. So we need to provide the transverse reinforcement along width of the footing. That is, we know the what is width. Suppose if you consider this as the total thing, so along width is nothing but this one. So this is along width. So this reinforcement we have to find out. Okay, so this reinforcement we have to find out. So in order to find out this reinforcement, again, this reinforcement has to be found out under column 1, and the reinforcement has to be found out at column 2, and then we need to check for one-way shear and two-way shear. So why only under column 1 and column 2? If you observe this particular diagram, under column 1, you can see what is how much reinforcement you have to provide here. Okay, at this section we have to provide. I hope you can see the yellow color. Yeah, so here under column 2 and under column 1. Okay, from here the curtailment will happen. So the curtailment goes like this, and then the curtailment goes like this. Okay, that's how we need to provide the transverse reinforcement. This is along width direction. Okay, remember that this is along width direction. Right. So let us provide the transverse reinforcement under column 1 and column 2. Right. Let me go here. Let me just delete. Yes. So transverse reinforcement along the width of the footing. So first we have to find out the transverse reinforcement. Transverse. Right. So transverse reinforcement under column 1. That's what we need to find out first. So how to find out this one? First, we need to find out the projection length. Let me show you one diagram here. Yeah, this one. Right. So if you see this one, the column 1 and column 2, we know the projection span. So if you consider this dimension of the column, okay, let me draw that. Yeah. So if you consider this dimension of the column, it is A. Okay, the value of A is 0.3. And this side it is d by 2, and this side it is d by 2. and on all the sides it will be 2D. So A plus 2D and A plus 2D. That's how these A plus 2D values has come. Right. So from this, we need to find out the projection of slab. Okay, let us find out the projection of slab. Projection of slab in transverse direction beyond the face of column 1. Okay, beyond the face of column 1. So that equals to, what is the total width of the footing? Total width of the footing is 1.5 meters minus 250 mm. So what is 250 mm? Let me just check that. Is it 250 mm or something else? Just give me a second. Just a second. Let me check that. Where is that? Just a second. It will be somewhere here. We had found out that one 0.25 meters. Let me just check that. I think it should be somewhere here only. But anyways, it is, the value is 250 mm. I'll just check and let you know. But the value is 250 mm only. I remember that one exactly. Right. Anyways, so I'll just check and let you know instead of wasting time. So the overall width of the footing minus 0.25 divided by 2. So if you solve this one, you will be getting the projection span. So projection span equals to 0.625 mm. Okay, that is projection of slab in transverse direction beyond the face of column 1. That's 0.625 mm. Now width of, or width over which column load is to be distributed. Width over which column load is to be distributed. That is B dash equals to 0.25. Okay, 0.25 plus 2 times of, let me just check that, 2 times of what is effective depth. We have taken 300 something. Yeah, 392. So 0.25 plus 2 into 0.392 mm. So that equals to 1.034 meters. That's a width over which column load has to be distributed. And then net upward soil pressure. Okay, net upward soil pressure equals to the total load from column 1. Okay, that is 300 kilonewtons. The total load coming from column 1 is 300 kilonewtons divided by 1.034, that is B dash value, into the width of the footing, that is 1.5. So if you solve this one, you are going to get the net upward soil pressure only under column 1. Okay, this value is only under column 1, that is 193.42 kilonewtons per square meter. This is the soil pressure under column 1. Now we need to consider it for 1 meter strip area. Okay, then we can do it for calculation. So moment at face of column. Okay, moment at the face of column equals to 193.42 into 0.625. 0.625 whole square divided by 2. Like that. 0.6 WL square by 2. That's the concept here. W is nothing but the pressure. Let me just write that. Yeah, 0.625 divided by 2. So that equals to 37.78 kilonewtons meter. Okay, that's the moment at face of the column. And from this, we can calculate the ultimate moment. Mu equals to 1.5 times of 37.7. Okay, 37.78, that will be equals to 56.68 kilonewtons meter. So from this, we can calculate the effective depth in transverse direction. Effective depth in transverse direction. Yeah, small d equals to the overall depth, that is 450 mm, minus the clear cover, that is 50 mm. So along the transverse direction, we are considering the diameter of bar as 12 mm. So 12 divided by 2, half of diameter of bar, that equals to 382 mm. That is effective depth in transverse direction. So based on this, we have to calculate the area of steel. So we know the formula for area of steel calculation, this one. So AST equals to 0.5 FCK by Fi, same thing. The only thing that gets changed is moment. Okay, moment is this one, whatever the value that you are getting here, which is 56.68, where B is the width of the footing. So here in the value of B, you should not take it as 1500 mm. Okay, so we are doing the calculation for 1 meter. Let me write that so that we can remember that. Okay, so calculating the values for 1 meter span, let me write in that way. Let us consider 1 meter wide strip for design calculations. Right. So from this, we can get the value of B, which is B equals to 1 meter, that is 1000 mm, and D, that is effective depth, equals to 450 mm. Sorry, okay, BD, that is 382 mm. Okay, so from this, we can get the AST value. So therefore, AST equals to, it will become AST equals to 420.78 mm square per meter length. So per meter, we have to provide 420.78 mm square of steel. That's the area of steel. So from this, we can calculate the AST minimum, that is minimum reinforcement. So we know the formula 0.12% B into capital D. So what is B value? 0.12% into B is per meter length we have to find out. So 1000 into the overall depth is 450 mm. So that equals to 540 mm square per meter. So this is the minimum reinforcement that we have to provide. So how much we have to provide? 420. But what should be the minimum reinforcement? For 540. So you have to provide 540 only, because 420 is less than 540. So we have to satisfy at least minimum reinforcement. Okay, we have to satisfy at least minimum reinforcement. So from this, we can find out the spacing value. So spacing S equals to area of one bar, that is 113.06. What is 113.06? We are providing 12 mm diameter bar. So pi by 4 into 12 square will give us this one. Area of one steel bar of 12 mm diameter divided by the spacing. Sorry, the total minimum reinforcement, that is 540 into 1000. That is B value. So that equals to 209.25 mm center to center spacing. So we can consider this value as approximately 200 mm. Okay, so that's the reinforcement that we have to provide. So area of steel provided equals to area of steel provided equals to, so 113.09, okay, 113.09 divided by 200, that is spacing, into the width, that is 1000 mm. So if you solve this one, the total area of steel provided will be getting, that is 565.45 mm square per meter. That is per meter length, we have to provide this one. So instead of 1000, you can directly consider the width of footing also. There is no problem. So here I'm just considering it as for calculation purpose. Okay, right. You can also directly consider the value of B as 1.5 meters directly. Instead of per meter calculation, you can directly do it for 1.5 meters as well. There won't be any problem. Right. So from this, the percentage of steel we can find out. PT equals to AST by BD. What is AST? 565.45 divided by B, that is 1000, into D. What is D? Overall depth, which is 450 mm, into 100. So that will give you 0.126%. That's the percentage of steel. Similar calculation, we have to do it for the column 2 also. Okay, projection of transverse reinforcement under column 2. Similar calculation under column 2. Same things will be there, but some minor changes will be there. Let me copy this entire one and I'll just replace it instead of writing all the things. Right. So projection of slab in transverse reinforcement, transverse direction beyond the face of column 2 equals to, okay, beyond the face of column 2 equals to 1.5 minus, what is the size of the column 2? It is 300 mm. That is 0.3 divided by 2. It will become 0.60 mm. And then width over which column load is to be distributed, B dash equals to the width of the column is 0.3. Okay, the width of the column is 0.3 plus 2 into 392, which is the effective depth. So this will become 1.084. Right. And then net upward soil pressure equals to the load on column 2 is 500 kilonewtons divided by 1.084 into 1.5. Right, that's fine. So it will become 307. 307.50 kilonewtons per square meter. Right. So here also we can consider the 1 meter strip length and moment at face of column equals to 307.50 into 0.6, this value. Okay, 0.60 square divided by 2. And if you solve this one, it will be 55.35 kilonewton meter. So, and then ultimate moment equals to 1.5 times of 55.35. So it will become, let me just calculate. So it will become 83. Yeah, 83.025. Right. And then effective depth. So 450 minus 50, it will be the same. That is 382 mm. And area of steel, that is also fine. I mean, no, the moment value is getting changed. So the area of steel AST will become 623. 623.38 mm square per meter, and AST minimum, that will not change, it will be the same, and spacing value 113.06 divided by 623. 623.38 into 100 into 1000, that is width. It will become 181 mm. So we can round it off to 150 mm maybe, or 160, 170, any value. So I'll just round it off to 150 mm. Right. And then the percentage of area of steel provided, this value will become 150. And then this will become 753. 753.7. And then the percentage of steel, okay, PT. So PT equals to AST by BD, that is 753.7 divided by B is 1000 into capital D, which is 450 mm. If you solve this one, it will be 0.167%. So that's the area of steel we have to provide along the transverse direction, both under column 1 and under column 2. So with this, we have calculated the shear calculation or shear reinforcement calculation, both in the transverse direction as well as in the longitudinal direction. Now we have to check for one-way shear. That's the last one. Okay. So check for one-way shear. One-way shear calculation is simple, as we have done previously. So here also in one-way shear calculation, just like the two-way shear calculation, where we have calculated the two-way shear, wherever the maximum shear force is coming, in that portion we have found out the shear calculation. So here also one-way shear also has to be calculated under column 2 only, not under column 1. Why? Because column 2 is experiencing the maximum shear force. Okay, column 2 is experiencing the maximum shear force, and hence we have to calculate the one-way shear and two-way shear, both one-way shear and two-way shear has to be calculated under column 2 only. Remember that. If you are getting the maximum value under column 1, for different scenarios, then you have to do it for column 1 only. So whichever column is experiencing the maximum shear, under that column only, we have to calculate both one-way shear and two-way shear. I hope it is clear. Right. So check for one-way shear, and we know the critical section will be at a distance d from face of the column. Okay. So since, let me write that, since maximum shear force is acting under column 2, therefore we have to consider shear calculation under column 2 only. Right. So the critical section will be at a distance d. That's one way shear critical section distance will be at a distance d from face of the column on all the four sides. Right. So we know how to calculate this. So capital V, shear force capital V equals to upward soil pressure into width of the footing. Let me write that. Upward soil pressure into width of the footing into projected length beyond D. That is the distance, critical section. So upward shear force capital V equals to 88.89, that we know, and width of the footing also we know, that is 1.5 meters, and this one we have to find out. Projected length beyond D. Let me show you one diagram. I have already drawn that one. Let me just have the diagram. Yeah, this one. This one. So this is the projected span that we have to find out. I hope it is you're able to see this one. Right. So projected span beyond D. This is the projected span beyond D. This distance. Okay, this distance is the projected span beyond D. So how to calculate this? So we know from here to here, the distance is 1.5 meters, and then we know the value of D also. Okay, we know the value of D as well, and we also know the side of the column face as well. So 1.5 minus 0.3 by 2 minus the effective depth. So that's how we can calculate. It's a simple calculation. You can also check it out later. So that will become, so 1.5 minus 0.3 divided by 2. Let me write the entire thing. 1.5 minus 0.3 divided by 2 minus 0.392. That's the width beyond the face of the column, that is D. So if you solve this one, the value will be 127.73 kilonewtons. So from this, we can calculate the ultimate shear. That will be 1.5 times of 127.73. That equals to 191.6 kilonewtons. From this, we can calculate tau V, that equals to VU by BD. What is VU? 191.6 divided by B into D. What is B? Width of the column, that is 1500, into D, that is depth of the column, that is 392. And if you solve this one, you will be getting the value as 0.326 megapascals or Newton per mm square. So in order to find out tau V is less than tau C or tau V is greater than tau C, we need to find out PT, that is percentage of steel. So I'll just write these ones. You can just do the calculations whenever you are free, but make sure to do the calculation because these calculations are required when we are doing the software design. These values we need. So make sure of doing this ones. So I'll ask you once we do the software design of combined footing. So make sure of having those values. So find out the PT value, that is percentage of steel, and then use table 19 from IS 456 2000. Okay, use table 19 from IS 456 2000 and obtain the value of tau C. Okay, let me write that. Use table 19 from IS 2000 and obtain the value of tau c and check whether tau v is less than tau c or not. So as far as my knowledge, tau v will be less than tau c only. So there won't be any problem. So there is no need of revising the depth and depth of the footings. But make sure to have the values of tau v and tau c. Okay. So this is something which you have to do on your own. Right. So that's the entire design of combined footing. It's a lengthy one because we have too many critical sections and too many shear forces and bending moments. So we need to design the reinforcement. The reinforcement calculation itself is the longest one. Apart from that, nothing else is the factor. So why we need to calculate reinforcement that much? Because we have the bending moment patterns in a different way. If it is only one column, there won't be much different bending moment patterns. If it is two columns are there, so we have different bending moment patterns. Now assume yourself how much calculations will be there for a mat foundation or for a strip foundation, not for strip, mat foundation or raft foundation. Why? Because on the same slab, we have number of columns. And on all those columns, if the load is same, then there won't be any problem. If you do it for one column, then all the other columns will also be fine. But each column is having different loads. Then you have to solve for all these scenarios. Okay, so that's the design of combined footing or manual design of combined footing. In the next class, we'll see how to design a sloped footing. Okay, that's the next one that we are going to see in the next class. Either you can also call it as sloped footing or trapezoidal footing. That we are going to see in the next session. Right. So that's from my end for this particular session. If you have any doubts, you can unmute and ask the doubts. Thank you.